this lecture we continue the discussion on cell control and just in time manufacturing. In the previous lecture we defined just in time manufacturing as a manufacturing system where the goal is to optimize processes and procedures by continuously pursuing waste reduction. The important words in this definition are waste and reduction and continuous. So, the main objective is to reduce or eliminate waste, and we define waste in the next bullet. More importantly, it is not a one time activity, it is a continuous activity which is stressed by the word continuously pursuing waste reduction. The net result is to optimize the processes and procedures, and through optimization we achieve higher efficiency and productivity as well as lower cost. So, explicitly cost minimization is not shown as the only objective. The objective is to optimize the processes and procedures, as a result of which we can achieve cost minimization as well as throughput maximization and productivity maximization through waste reduction and continuously pursuing waste reduction. We also defined this definition for waste. So, waste is anything other than the minimum amount of equipment, materials, parts, space and time which are absolutely essential to add value to the product. So, any effort over and above the minimum required which is spent on an activity is defined as a waste, provided it is not able to add value to the product. We also mention this, that JIT or JIT is less of techniques and more of a philosophy involving total quality management, employee empowerment, zero inventories and pull systems. We saw some aspects of total quality management and employee empowerment in the previous lecture. We will continue the discussion on zero inventories and pull systems. Now, one of the reasons that just in time manufacturing picked up was because manufacturing companies had a lot of inventory lying in the workplace. It was quite common to have anything between 3 to 6 months of inventory in the system, which was very large in terms of quantity, in terms of money, and was affecting the performance of the system both from a financial viewpoint as well as from an operational viewpoint. So, organizations felt the need to have better control, and that is the reason you will find that the title of this lecture is cell control or production control, and just in time manufacturing can also be seen as a way of production control, though its scope is far higher than only production control. So, there was a need to control the inventories, and the extent of inventory had to be brought down in organizations. Many reasons existed for the increase in inventory, and these reasons are also well known. One of the main reasons is uncertainty, particularly uncertainty in the demand. The easiest way to counter uncertainty is to have inventory, and it became common practice to increase the inventory so that any fluctuation in demand or uncertainty in demand could be met comfortably. A second reason for large inventories was insistence on economic order quantities and economic batch quantities. Now, the economic order quantity formula and economic batch quantity formula are well known. So, the economic order quantity formula is given by root over 2 D C naught by C C, where D is the annual demand of the item, C naught is the order cost for the item, and C C is the inventory holding or carrying cost for the item. Now, using these data, one would get what is called the most economic order quantity, or the quantity for which each order has to be placed such that total cost comprising of order cost plus carrying cost is minimized. Now, this formula is easy to use, and people started using this formula to determine their economic order quantities and rounding off these quantities to comfortable integer numbers such that orders can be placed for such numbers. Now, while the economic order quantity can be different for different items, when the ordering took place, people did not take this into consideration. Now, different items could have different demands, and even if the order cost and carrying costs were different, the economic order quantity would be different for different items, even if the order cost and carrying cost are the same for certain number of items. So, because the demand is different, the economic order quantity was also different. So, if several items were bought to make or assemble a product, each one of them now had different ordering quantities, and therefore, there was either excess inventory of one or there was shortage of another. The ordering quantities did not synchronize, and this led to higher inventories. In a similar manner, the economic batch quantity formula, which in consistent notation will become 2 D C naught by C C into 1 minus D by P, where C naught now is the setup cost here, D is the demand, this is the inventory holding cost, this is the same demand here, this is the production capacity. So, D by P is a fraction less than 1, so that 1 minus D by P is positive, and we get a positive number here. So, this formula gives us the economic batch quantity, which means what is the best batch quantity to run a particular production batch. Once again, since demand for each of these items are different, the economic batch quantities would also be different for different items, which led to a lot of work in progress inventory, while this led to raw material inventory or inventory at the store. Even though advanced models existed for synchronizing the order quantities for various parts, or for synchronizing the production batch quantities for various items, the economic lot sizing formula takes care of some of these. Many times the more difficult part of synchronizing the purchases and synchronizing the production batches were not taken into account, and therefore EOQs and EBQs increased, and not only did they increase, they were different for different items, resulting in very large amount of raw material as well as work in progress inventories. Third is large value of C naught. Now, here the term C naught in the economic order quantity formula, which means when items are purchased, C naught represents the order cost, and in the batch quantity formula, when items are produced, C naught represents the setup cost. Now both the C naught as ordering cost or C naught as well as setup costs were very high. C naught as setup cost was very high because the time taken to do setups and changeovers was very high, therefore C naught was very high here. In this many times C naught was very high because C naught would also involve costs like transportation, inspection and so on, and these are quite expensive and therefore C naught became very high. So when the value of C naught is high, automatically the value of Q is also very high. So large value of C naught was also a reason for large quantities to be ordered or produced, which resulted in large inventories in the system. Fourth is also availability. Particularly in the context of ordering. So there would be situations where the availability was a kind of a restriction, and when very few suppliers were there and when the material was available with the supplier, it was necessary to buy them in large quantities. So availability dictated purchase of large quantities. The fifth reason also would be discount, which forced buying of large quantities here. So we have studied inventory models considering discount. So this economic order quantity formula is modified to include discount, and when we consider discount we particularly end up buying a very large quantity. Two types of discounts exist. One is the all quantity discount, the other is a marginal quantity discount. Particularly when we use the marginal quantity discount, we understand that the marginal quantity discount leads to larger ordering quantities. Even though there is a certain optimization that takes place in deciding the order quantity under marginal discount condition, and the best value of Q, the order quantity, is chosen based on an optimization, it still leads us to buying large quantities, which result in the presence of a large amount of inventory in the system. Availability of lot of space amongst the machines or within the storage area, when lots and lots of space is available, there was always a tendency to use space by filling it up with inventory. So people started increasing the inventory that they had through, because lot of space was available. Last but not the least, the main reason why there was a lot of inventory that was available was because people believed that anything that is produced will be sold, and therefore it is not wrong to produce in large quantities, keep them and sell them when they are demanded. So when this led to the feeling that one need not produce to the current demand, but one produces to an aggregate demand, which meant that we were following what are called push systems, produce to forecast, produce to aggregate demand, produce large quantities and make them available when the demand actually comes. So this led to producing in very large quantities. So all these are reasons for large amount of inventory. This is indicative, it is not exhaustive, it is reasonably exhaustive. There could be other reasons that also exist because of which large amount of inventory is being held. So because of all of these, organizations had at least about 3 to 6 months of inventory, and organizations felt that this inventory has to be brought down. So, there was a systematic exercise which almost every organization carried out to bring down this 3 to 6 months inventory to a manageable 1 month inventory. Actually bringing the inventory down from 3 to 6 months to say 3 to 6 weeks is difficult, but not very difficult, whereas bringing it down from 6 weeks to 2 weeks or 2 weeks to 1 week is very difficult. So, what happens is organizations progressively gave themselves deadlines of saying that from 6 months I bring it down to 6 weeks, and then I try to bring it down to 1 week, and if possible I bring it down to 1 day, and so on. So, the ideal situation that we could think of is called I have 0 inventory. When I produce something, we did see some aspects of single piece transportation and single piece production. So, the ideal situation is a single piece production, and the only inventory that I have is that piece which I am currently producing. So, this leads to a very ideal situation called 0 inventories. Bring down the inventory to 0. It is an ideal situation. We know that we cannot have 0 inventory in any plant, nor can we have only that piece which is being produced in the system, but 0 inventory is like an ideal target which we would all the time try to achieve. Whatever be the present state of the system, it will be worse than the 0 inventory, and a 0 inventory target would actually give us the motivation to try and get better than the current position or situation that the organization is in. So, this is the ideal situation called 0 inventory, which is a very integral part of just in time manufacturing. The other thing that organizations did is called push systems. So, traditionally organizations used what is called push system. Versus pull systems. Push systems are traditional, where push systems work with forecast. So, based on the previous data, as the demand for the next periods are forecasted, and since forecast also has a certain accuracy associated with it, accuracy or lack of it, there could be forecast errors, then the aggregate forecast is taken to have the annual forecast based on which production plans were carried out. So, the annual forecast, the sigma indicates sum of the forecasts. So, an annual forecast is taken, and the annual forecast is divided into production plans, and production schedules. And most of the times these decisions were based on the economic batch quantity or the economic lot scheduling model. Now, these used the formula Q is equal to root over 2 d C naught by C c into 1 minus d by p, which was written earlier, and once again C naught used to be large because setup times and changeover times were large. So, order quantities were large. Not only were order quantities large, even if we take a very simple system where there are two parts that go into an assembly, if we say the batch quantity for one of them is Q1, the other one is Q2, Q1 and Q2 will not be equal, and therefore the assembly would always produce minimum of Q1 comma Q2. And if we assume that Q2 is more, then there is an inventory buildup here. Now what is expected is that since Q1 production quantity is less than the production quantity Q2, Q2 being slightly more, the production cycle for Q1 would be little less than that of the production cycle for Q2. Now this production cycle will start operating immediately. So as these items come in, now from the inventory this will be taken and this will be used. For example, this machine could produce some other item or product in between. Sometimes we could have situations where both Q1 and Q2 are produced by the same machine. So it will produce a large batch of Q1, because the layout was also more a process kind of layout with functional or department specialization. So this will produce a large quantity of Q1 and then keep it here, and then when it starts producing Q2, Q2 will feed directly, Q1 will feed from inventory, and then the minimum of Q1, the item starts getting produced. Then after a while it switches, it has produced a large quantity of Q2 now, so it has built up inventory, now it starts producing Q1 and then once again the item will come out. The only thing that will happen here is that at any point in time we will have a large inventory of Q1 or Q2. Now the next question is, can we have a system by which this cell makes Q1, this cell makes Q2 instead of a machine, and these two are separate and then they feed. Now when they feed, this will be producing at some rate, this will be producing at some rate. If we use the economic batch quantity model, the rates will not be equal, they will be unequal, but still the amount of excess inventory that is getting built up will be less, because these are producing in parallel and they can feed into the assembly. Now the next thing, if we really want to minimize the inventory, is to let them produce at the same rate, so that there is no build up here and the items come out. So the only reason why this could not be done is because this would involve creating some more facilities or buying some more machines and keeping it there. And when we start doing that, in some way the utilizations would come down, because earlier what a single machine could do, now two machines are doing. So automatically the utilization will come down here. So the emphasis on measurement was more on utilization than on output. So when in order to create something like this, it is now necessary to change the measurement, which is from utilization to output. So the measurement is now changed from utilization to output. Now how do pull systems work? Pull systems do not produce to forecast, but essentially try to produce to demand. So they try to produce to demand. So when you try to produce to demand, you tend to get estimates of daily demand. Now today it is a little easier to get estimates of daily demand than 10 years ago. The reason being, the ability to capture information is much better today than it was 10 years ago. Now today we have supply chain management principles, we have point of sale capture of data, we also have ways by which customer preferences are learnt, and therefore these things get translated through advanced packages such as ERPs and other SCM packages into demand. And there is a lot of data analytics and data mining that happens, which gives everyone a feel of what is the demand for the day. So, the demand for the day or demand for any period can now be estimated quite accurately, and now the production is based only on demand. So, when the production is based only on the demand, let us say the demand is 100, let us say the demand is 100, then it is enough to produce 100 of this and it is enough to produce 100 of this. So, the insistence on the economic batch quantity goes away. Now, because we are producing in quantities other than the economic batch quantity, so one might get a feeling that we are not producing them optimally. The economic batch quantity for this could have been 125, the economic batch quantity of this could have been 200, but we are producing only 100. So, one would get a feeling that I am losing out on some aspect of optimization here, but the gain is that we are able to produce an equal quantity, there is no build up of inventory here, the items come out and they are sold. So, the measurement now shifts towards throughput and sale, the measurement is not about cost. So, when the measurement was about cost, then one would add the total cost of producing these two using the EBQ formula and using production quantities like this, and then we would realize that EBQ was more cost effective. But today organizations are willing to use this and finish the production in time. So, if we measure time, this system will be much faster to produce than insistence on the EBQ. So, with pull systems coming in, all these disadvantages are overcome, production quantities become smaller, and when production quantities become smaller, the inventories that are there in the system also become smaller. More importantly, in pull systems, organizations move to what is called make daily and sell daily. So, make daily and sell daily. Once again, this is close to an ideal situation. There could be some issues with respect to this. When we follow the model make daily, sell daily, we are indirectly saying that we should not hold inventory at the end of the day to meet the next day's demand. If, for example, the capacity is 100, now today's demand is 80, tomorrow's demand is 120 and the capacity is 100. Now, if we follow strictly the make daily, sell daily discipline, we assume that we do not know this information because this is going to come tomorrow. Today's demand is 80, my capacity is 100, so I can make 80 and I can sell today's demand. But tomorrow's demand is 120. So, when tomorrow's demand strikes me, I quickly understand that my capacity to make is only 100 and not 120. Now, will I be willing to forego that 120 demand? I cannot afford to do that. At the same time, I know that if I had aggregated these two, my total demand is 200. So, I could make 100 today, sell 80, keep 20 for tomorrow and make another 100 tomorrow and meet the 120. So, once again make daily, sell daily is an ideal situation. It is a very good situation that one has to look at, and this situation is achievable if the variation here is less. If the variation here is less. At the same time, I cannot build 120 capacity here because 120 is the bigger number of the two. One of the reasons I went to this is because the variation was higher. Now, if I want to implement this, then I have to have a less variation in these, which is explained by the first bullet, exposes problems caused by variability. So, when there is variability, pull systems suffer. Pull systems require that the variation is less. The ideal situation is all daily demands are the same and equal to the capacity, but that is something which we cannot achieve. So, in situations where the variation is slightly less, these kind of streamlined production systems work very well. Organizations will, however, meet this 80 and 120 by holding a small amount of inventory. So, organizations will tell themselves that I will go up to a maximum of 10% that I can keep, and I do not keep it for months, I may just keep it for 1 or 2 days, so that I meet instant fluctuations. Though the motto or the philosophy would be to make daily, sell daily, organizations understand that certain amount of inventory is unavoidable, otherwise you will not be able to meet demand and you will sell less and the entire profitability will go. So, some of these things such as 0 inventories, 0 defects and make daily, sell daily are all ideal situations for which the organization will always aspire to achieve. Now, we get into what are called the basic elements of a JIT system. So, a set of basic elements are listed here, starting with pull or Kanban controlled production system, small lot production, quick setups, flexible resources, cellular layouts, uniform production, quality at source, productive maintenance and supplier networks. Now, all these are seen as some of the basic elements to implement a just in time manufacturing system. Now, let us go through each one of them, but in a slightly different order, even though the order given here starts with Kanban production control system. Now, we could start with cellular layouts, because we have seen a little bit of cellular layout. From there we would get into flexible resources, and then we would get into small lot production, quick setups and Kanban taken together, and then we would get into quality at source, productive maintenance and supplier networks. So, let us first begin with cellular layouts, because we have seen so much of cellular manufacturing in this lecture series. So, let me explain the cellular layout first and then add So, let us say we have cellular layouts. So, let us take a very simple case of 2 cells feeding 2 parts to an assembly. So, a cellular layout would look like this. Machines of course will be here. So, there will be machines here. In fact, I would even use different colors to show that the color machines are the same, but they are in different cells. So, the simplest advantage of cellular manufacturing is something that we have already seen. So, if these two, let us say we call them as P and Q, are 2 parts, or if it makes a single product, so let us call P1 and P2 as the 2 parts that will go to the assembly and finally give us a P. Now, if we do not have a cellular manufacturing system, then we would have a system like this, where we would have a system like this where all the blue machines were here, all the yellow machines were here, and all the red machines are here. And these could even be separated by a kilometer or two. So, each of these would now move from a blue to a red to yellow and out and so on. This kind of a thing we have already seen. So, the cellular layout very quickly brings all these machines together, which enables what we call as a single piece flow. I have explained single piece transportation and single piece production in one of the earlier lectures. So, this enables single piece flow in this system. Now, when it brings single piece flow into the system, it automatically improves the throughput. Because material transportation is easily taken care of, the time taken to produce within a cell is far smaller than the time taken to produce if it moved from one machine to another and it moved large distances to do that. So, cellular layout facilitates a whole lot of things to achieve in a just in time manufacturing system. And we have already seen that cellular layout would involve flexible resources. In terms of machines, in terms of people, and also in terms of processes, an aspect which we have not stressed upon till now in this course, which I would possibly do now. Now, if we take this cell, the first place, this cell would have machines which are functionally dissimilar. So, if it is a labor intensive cell, then it is necessary, and if we use a rabbit chasing or dedication method, it is necessary for operators to be able to handle a variety of machines, and therefore, we need flexible resources in terms of operators. Now, even though these resources, these machines are functionally very dissimilar, at some point in time they also should have the capability of substituting or carrying out some operations in the event of some emergencies, and particularly if they are sophisticated and advanced machines, then they will be flexible enough to handle a variety of operations. So, flexible resources in terms of machines and in terms of people. One of the strengths of cellular manufacturing is the fact that not only are the production processes or production decisions simplified in the cellular manufacturing, production support or manufacturing support should also be simplified or is also simplified in the context of cellular manufacturing. Now, what are these manufacturing support? Now, if we look at manufacturing, the central portion is called core manufacturing, and then we have something called manufacturing support, which is outside of this, and manufacturing support would involve quality, maintenance, stores, finance or accounting, and so on. Now, these are all activities which are needed for the cell to function. Now, many times we would create cells and give a lot of control to each of these cells, but there would be times when these are not decentralized. Now, one way of looking at cellular manufacturing is to kind of decentralize the whole process, so that processes become simpler. Many times we will see in organizations that these are not decentralized, whereas there is a need to decentralize all of them. For example, one could say that for this cell, the quality group could be divided into 2 or 3 groups, and say one group will be in charge of quality for these 2 cells, some other group will be in charge of quality for some other cells. Similarly, the accounting systems, the maintenance, the stores can also be made smaller and dedicated, just as machines are dedicated, so that better control and performance of the cell happens. That would also involve additional resources. Just as when we did this, we realized that additional machines may be required. Now, when we do this, we also realize that additional resources may be required, and then organizations will have to take care of these. Now, to continue this, now outside of this is the supplier. Now, this side is the customer, and somewhere is the R&D, the research and development, which changes or provides inputs to this. The supplier invariably comes here, quality, accounts. The customer also comes, there could be marketing and sales, purchase. So, the supplier comes here, sales comes here, quality comes here, and so on. So, all these will now have to be decentralized, and the cellular manufacturing systems have to be made simpler, so that they perform extremely efficiently. So, we have seen some aspects of flexible resources and cellular layouts. Now, we will start looking at things that are related to that. So, first we saw cellular layout. Flexible resources, small runs. Small runs or small lots is possible. In this, we have seen examples of small run, particularly when we saw 2 aspects in an earlier lecture. We saw single piece flow in terms of transportation and production. Implementing a single piece flow system in transportation makes the time to produce a little smaller, because of which either an additional item in terms of variety can be produced, or the volume of production can increase. The other one that we saw is single piece flow in production, where we gave an example of a batch size of 10, but there were 4 parts, and we said we would do P3, P4, P2, P1, followed again by P3, P4, P2, P1, which meant that 4 parts are now produced in 8 batches, each part having 2 batches, with batch size being 5 instead of 10. Now, that is an example of small runs or small lot production. Now, small lot production is enabled here largely because the time spent on transportation is also much less. Now, when we did that example in a previous lecture, we also found out that when we did production batches of 5 instead of production batches of 10, the total time to produce was increasing. The reason for the increase was, if we were making 4 parts and each in a batch of 10, there would be 3 or 4 changeovers. If we start making them in 8 batches, each with a batch size of 5, there would be 7 or 8 changeovers depending on whether we want to come back to the starting part. So, the number of changeovers increases. So, when the number of changeovers increases, the time taken to produce also increases. So, if we do not want that time taken to produce to increase considerably, it is necessary to have a smaller time for setups. So, we move to what is called quick setups or quick changeovers. Every system that implements just in time will concentrate on reducing changeovers or changeover times. By reducing changeover times, we will be able to achieve single piece production flow, and single piece production flow is a necessary thing to strive at if one is using just in time manufacturing system. So, we need to look at pull or Kanban control system as the fifth one here, pull system or Kanban controlled system. Which we will do a little later. We move now to the last 2 or 3 things there. We now look at what is called uniform production. I have already given an example for uniform production. When I gave this example, I said that if there are 2 ways of looking at uniform production. One is if I, with the example that I gave, where if my capacity is 100 here and my demands for 2 consecutive days are 80 and 120, and if I am willing to maintain a small amount of inventory here, assuming that this variation is not very large, I produce a uniform quantity of 100 here, so that I am able to play around with very minimal inventory and yet meet the demand. Another way of understanding uniform production is, if this 100 capacity is for 3 products, and let us say I could make 50 of A, 30 of B and 20 of C in a day, where A, B and C are 3 products that I can make, or 3 varieties of the same product that I can make, then one thing I can do is I can have one batch of 50 of A followed by 30 of B followed by 20 of C. Which, or I could think in terms of 25A, 15B, 10C, another 25A, 15B and 10C. Now, this would mean I am making 6 batches. Now, actually if my batch size, minimum batch size is 5, I can go for 10 plus 6 plus 4 up to 20 batches I can produce. If I provided I have quick changeovers and I have the time to change over 20 times within a particular day by having quick changeovers. Now, this uniform production at the end I could do, for example, so instead of doing 25A, 15B, 10C, I could actually do something like, this is 5A, so 5A, 3B, 2C 5 times for this into 2. So, I could do something like A, B, C, 10 times, again followed by A, B, C, etc., and I could do this 10 times to meet this. So, this would give me something like a uniform production in my system. Now, all these are enabled because of almost all of these which are above this thing called uniform production. We still have not seen much about the pull system or the Kanban system, as well as about aspects of quality, maintenance and supplier. Now, we will see all those aspects in the next lecture.